I want to thank you for coming. This is a real thrill. So Sunil and I did meet 16 and a half years ago, and I'm not going to go into as long as Sunil did because I got an hour's worth of talk to do, or 45 minutes. But you guys are terrifically lucky to have him here. I cannot tell you what a steal you've done, and what a hole he's left at Case. And I was telling him this morning that I'm trying to fill in those pebble by pebble, but it's going to take a long time. Yeah, this is all new. It's based upon many, many years. I turned 62 in June. Many, many years of frustration, kicking things around. This solution that you're going to see today literally came to me when I was getting out of bed one morning. You work with a problem long enough, and sometimes it'll happen. So there was that aha experience. And I've put it together in a fairly jazzy talk, as you'll see. And I've got some money up here. These are uncirculated dollar coins. It's a trademark of mine. I've got 2 here, and I've got a roll of uncirculated ones that I'm willing to break for good questions and good comments. So I do pay. My wife was not all that happy when 500 of these arrived in the mail one day from the U.S. Mint. And she said, "What are these?" And I said, "Well, I give them away when I teach and stuff." And she goes, "You do what?" And then I had to tell her that for years I've been going to the bank at $20 a time and getting 20 of these and doing it. But it works. It works very effectively. So you can be bought. All right? And I appreciate it. So this is all about a discussion between 2 characters. You've already met Maxine, stat scientist. Obviously, she's my alter ego. And today she's going to work with a clinical investigator named Will Treatwright, MD, PhD. And Will today he's an expert in tropical diseases. And so we can couch everything that I'm going to do in terms of the conversation between these 2 people. It frees me from being as preachy as I usually am. Now I can preach through Maxine. So Will says, I heard you're developing a new schema that takes your March of Science notion for sample size analysis and extends it to data analysis. And Maxine says, yeah, that's correct. I'm quite excited about it. Are you ready to show it to others? Yeah, but I only have about 45 minutes today. All I can do is show examples. I don't have time to give the mathematical basis to show you the evidence that it really works. And then Will Treatwright, MD, PhD, comes back and says, perfect. When statisticians enter math land, they lose me. Yeah, great. This gives me another opportunity to ensure that what I do is useful and understandable to researchers. And so what I'm going to say is what I do in these talks and everything that I do, collaborating and consulting is my laboratory. It's where I get my ideas. It's where I test them out. It's why I like to come down here, especially in March. If you saw the weather in Cleveland today, and I get to stay with my best friends in the very whole world from graduate school and all that kind of stuff. But this is my laboratory. So whatever comments you have, I take back and things get worked out. All right? So Maxine says, I'll use your study on Furlingia as an example. Now, I'm not going to tell you where Furlingia comes from because I have all kinds of things that remind me of things that happened in the past, but I will tell you where Furlingia comes from. Furlingia is a derivative of a Dr. Furling that I had as an undergraduate, and let's just say I didn't like him. And neither did any of the other students in the math department at Claremont McKenna College, and so I've now named a disease after him. So be careful. Be careful, okay? So please summarize it, says Maxine. So now we're going to summarize Furlingia. This is all about a statistical fable. I can work in all the teaching principles I need through a fable. It works very effectively for me these days. So Will says, I'm investigating whether or not a new treatment can reduce mortality rates in young children infected with a tropical disease called Furlingia. Now what I want to tell you is this is just a pseudonym for malaria, okay? So this is very similar to malaria. Furlingia is a tropical disease that infects mostly young children during the rainy season. Its incidence rate, about 3%, will contract severe Furlingia before reaching age 5. Usual care is hospitalization to treat high fever and dehydration. And mortality rate for Furlingia, for severe Furlingia, is about 40%. So 3% of the kids will get it, 40% of those 3% will die. This is true of malaria. If you don't know, it kills about 1 million kids a year in sub-Saharan Africa. It's like flying a Boeing 747 into Mount Kilimanjaro, 7 Boeing 747s into Mount Kilimanjaro every day. It's still a disease that racks us. But this is for Lingia, okay? Experimental therapy is BIOS 266. The last time I gave this talk was down in Chapel Hill, and I gave it to Roe Incorporated. Roe Incorporated was founded by Ron Helms. Ron Helms was the best stat professor I had ever, and Biostat 266 was the linear models course that I've told you about 1,000 times, Sunil, and what set me straight in terms of modeling and all that kind of stuff. So I named the course, I named the therapy after the course that Ron taught. Mortality, defined as death within 30 days. So we got a very simple endpoint here. This is not a survival analysis. This is just whether or not they make it to 30 days. Keeps everything simple. Dropout rates are less than 3%, and now we get to say non-informative. I get to make up the fable, so now I don't have any problems, right? Don't have to deal with and bad missing values. So here's a design. We're going to take a sample size of cap n, divide it into 2 pieces, little n1, little n2. We're going to randomize, all right, put n1 over there into BIOS 266 and n2 into usual care. 30 days later, we're simply going to ask, did the kid live or die? Anybody have a problem with this design? It's about the simplest design I can come up with, and yet I can teach everything that I need to teach in here with this very simple design. So here's a new slide in here, a traditional hypothesis testing schema. I like to give this same talk to statisticians, even at the joint stat meetings. I give a similar talk. I'd give it probably in front of a group of transplant surgeons if they wanted to. So a little review here of what the traditional hypothesis testing scheme would be here. We've got a continuum mortality difference, Biostat 266 versus usual care. We would measure that. So we measure the kids that, what percentage of kids die under Biostat 266, what percentage of kids die under usual care. We set 0 as what I'm going to call today an exact null, all right, otherwise known as a point null, but today we're going to call it an exact null, and you'll see in a little bit why. And we've got data. We've got superior over there on the left-hand side, the superior range. We've got the inferior range over on the right-hand side. We're going to have some distribution now. You've seen this in every stat textbook. We're going to mark off some region over there at the 025. We're going to put another region over there at the 025. And let's suppose we got a result there on some t-test or whatever, result over there at, well, looks about 0.01, let's say. All right? And so that would be the 0.01. And we'd multiply that by 2 for reasons that we'll get into and I've never understood, okay? We'll multiply that by 2 and we'll get a p-value of 0.02, all right? And so where is Maxine coming from? Where is Maxine coming from today? Why did I start working on this problem, all right? Well, Maxine Chance believes, all right, that the usual 2-sided hypothesis schema rarely makes any scientific sense, all right? So she's saying, why do we usually double the p-value? This lumps 2 completely different hypotheses, say, Biostat 266 works superior, BIOS 266 is inferior, into a single alternative hypothesis. And she's saying it's never made sense to her. All right? So here's what she's saying. Well, we got this result over here, and it's superior, and it's a 0.02. But we got this result over here, and it's inferior, and it's a 0.02. Oh, but it's the same as this one over here, and it's the same as this one over here. And you know, I really don't understand what's going on here because you're treating these things as the same because we lump them all together. We say, oh, it's just not null. All right? So we've rejected the null hypothesis without regard to direction. So she says that's a problem. All right? She didn't like that. Dr. Chance also believes the common point null hypothesis is almost always implausible. Almost always implausible. So she says, why would anybody think that BIOS 266 and usual care have exactly the same mortality rates? Exactly. To the 20th decimal place, if you will. Why would anybody believe that any 2 groups have exactly the same on anything? Exactly the same. We need to be asking how much of a difference is there, all right? And that's why in my teaching I stress confidence intervals, confidence intervals, confidence intervals, which those of you who've studied both frequentist and Bayesian know that the frequentist confidence interval is frequently pretty close to what the Bayesians would do, okay? With the, you know, with pretty flat priors and those kinds of things. But let's concentrate on the difference. So here's our graph again, and what we're saying here is, I didn't do that very well. It's not showing up. There it is, exactly null. Let's get rid of that, and let's just bring our hypotheses in here and just say we want to know whether it's on one side of that bound or the other. And we're going to say the probability of being at 0, there's that touch of Bayes coming in there, is 0. We don't believe it. All right? For an example, so for years I've been saying, you know, I really don't care much about correlation. Here's an interval. I'm sorry. I'm off. All right? So I'm going to extend that now to an interval null hypothesis. An interval null. I'm going to say that, well, 0's in the middle of that, but I want some range around 0 to be in effect, all right, no difference. And I need to do this for some mathematical reasons that I won't go into. We just don't have time for that, okay? And it has to do with convergence and those kinds of things. But I need to have a region there that things can converge into if they happen to be in there. So I'm setting up what I call an essentially null region, okay? And on, we've got the superior and the inferior side, but we'd like to bring those in as well, all right? So you're either in this small region, you can define the small region. We'll have examples where we define it in various ways, or you're on one side or the other. One side or the other. We have basically two one-tailed things working here. Now, what I thought the slide was, I have done this all the time with correlation coefficients, because I've never believed, or I've never understood why anybody cared when they got a p-value out of SAS or anything else, and it told me that this correlation coefficient was different from 0. Like, who cares whether a correlation coefficient is different from 0? I want to know if it's sufficiently strong. Now, my number might be 0.3 in terms of strength, because when I see a scatter plot, it begins to have a little bit of a form at 0.3, but I knew I could probably be safe if I said that there really is no correlation between two things, okay? On a clinical side anyway, all right? Between -10 and plus 10. You can pick any region you want. I just picked this one to get us an example. So what I'm saying is if the measure we're looking at, or the statistic we're looking at is a correlation coefficient, maybe we put an essentially null region between -10 and +10, and then we move those in and we say, hey, if it's, you know, greater than or less than that, we're okay. So there's an example. Dr. Chance believes p-values are widely and dangerously misunderstood, all right? And this is a fact. This is an absolute fact, okay? She says, contrary to common belief, the p-value is not the chance that the null hypothesis is true. Not the chance the null hypothesis is true. She continues, both content investigators and statisticians behave as if a p of 0.02 means there's a 98% chance that the null hypothesis is false. All right? I know this is a fact. All right? They behave this way. They see a 0.02, they think, it's about 98% chance that it's false. All right? All right? So the lack of understanding leads to absurdly incorrect interpretations and simply bad decision making. We'll see an example of that. She also believes that Bayesian methods offer great ways to address these issues. But Bayesian methods have been slow to be widely adopted in practice. Why? Well, she says, although the computations involved are now feasible, they weren't when I was in graduate school, full Bayesian approaches require the team to pre-specify more about each question than they seem to be willing or able to do. There's just a lot of front work that needs to go on, all right, in order to get things right. If you just take this classical straight way of even comparing two proportions and you use two beta priors, there's 2 parameters for each beta prior. There's 4 parameters you've got to come up with each question. It's a lot of work. I'm going to show you an easier way that gets us mostly of the way there, almost all the way there, I think. That's what the touch of Bayes comes down to. All right? So Dr. Chance's mission is, in order to get good answers to more useful questions, we need to find a straightforward way to add just a touch of Bayes to common frequentist methods, So what's my rationale here? All right? We've got all these frequentist methods out there that people have been using for decades. They know them, they trust them, they like them or whatever. If we can spin them just with a little touch of bass and turn things around and get them to answer questions that are much better questions than the p-value answers, all right, then we're going to be a step ahead. So that's the mission. Whatever this might be, says Maxine, the pure frequentist will dislike its Bayesianism, all right? And the full Bayesians will think it's simply too simplistic, a cop-out. And I got stories that I could tell you already about that. I talked to Sunil about this about a year ago. He probably doesn't remember. And what he wrote back was in the email, it's right where you ought to be. Right where you ought to be between these two camps. If you can piss both of them off, maybe you're in the right place, all right? So here we go. So Maxine said, the scheme I'm going to show you stems from similar ideas that are now advocated for sample size analysis for study planning. Regarding sample size analysis, so I don't know if you know this paper, but it's written by, well, he sort of needs no introduction in the world of biostat. This is second author here and very much involved in this paper is Marvin Zelen. And Zelen was a pioneer in clinical trials. Founder of the Eastern Cooperative Oncology Group at Harvard, basically the founder of the Harvard Biostat Group. And he considers this notion that we're going to talk about today and what they talk about here in terms of sample size analysis as one of the most important concepts that young investigators want to know. I've heard him speak on it. All right? There's another chapter, a chapter that I wrote with my colleague from SAS when we wrote Proc Power and Proc GLM Power. We asked to write a chapter. And the same principles that Zelen talks about in that stat science paper, we incorporated into this chapter. I'd actually been using those principles for a long time. And when that chapter came out by Zelen, I said, oh, now I can do this stuff. I can do this crazy stuff because Zelen says it's okay. All right? If you write me, I can give you a copy of that chapter. I don't put it out on the web because it's copyrighted, but I can give you my LaTeX output, my PDF of my LaTeX. It looks almost identical to the article. All right? If you ever want that. So what's the big notion here? The notion is crucial type 1 and type 2 error rates. What's a crucial type 1 error rate? A crucial type 1 error rate, all right, I'm assuming you know what a regular type 1 error rate is. A crucial type 1 error rate, which I call alpha star, all right, if the test yields traditional statistical significance, if the p-value is less than alpha, what's the chance that this will be an incorrect inference? So we're flipping around, okay? We're flipping around the conditionality of the common type 1 error rate. Now you've got a significant result in front of you. What's the chance that it's wrong? Type 2 error rate, the same thing, all right? Type 2 error rate, the test was not significant. What's the chance that it's wrong? Flipping around the conditionality of a type 2 error rate. People are always asking me, so I've been giving these workshops and teaching these principles for like 15 years. People are always asking me after the workshop or even during it, because it's all about sample size analysis, can we use that same stuff that's talked about in the Lee and Zelen paper, or talked about in the O'Brien-Castello chapter, or talked about in other papers as well, all right? And some of you may know those. They've been around. Other people are writing on the same thing. Can we apply the same thing to data analysis? So what Will says, well, what do you mean, a crucial p-value? So what would a crucial p-value be if you get the drift? Well, the regular p-value is what? Regular p-value in sort of street talk, okay, is p is the probability of that you got the observed data given the null hypothesis is true, right? Whether it's a t-statistic or a chi-square, it doesn't make any difference. It's the observed data. So what would p star be? We're going to flip the conditionality. P star would be probability the null hypothesis is true given the observed data. That's really what researchers want to know. And that's what they think the p-value is, but it ain't. It ain't, all right? And so that's what the crucial p-value is. And then we have this one, of course, we go 1 minus p star. There's an example. So p star, if p star is equal to 0.02, given the observed data, there's only a 2% chance the null hypothesis is true. Isn't that direct? That's a direct statement, the kind of statement that most people like to know. Those of you in the medical field, this is very much, in fact, the mathematics, it's not high-level mathematics. This is just positive predictive value. This would be positive predictive value. 1 minus p star is the probability the null hypothesis is false, all right, given the data, all right? So positive predictive value, which would be the research hypothesis, is true. would be that way. So you get what a crucial P star would be, all right? Flipping things around, flipping things around. So an example, if, in other words, 98% chance the null is false. Given the data, 98% chance the null is false. Easy, easy. Yeah, my method addresses this, but it's become extended into lots more things, all right? It's basically what she's saying here. So what we're going to do is the whole 9 yards today. Not the math, all right? Not the math. I told you that. This is related to something that has a lot of attention out there, and it's related to likelihood ratio analysis, all right? And here's a great book on it by Richard Royal from Hopkins, Likelihood in the title. And here's another book that's come out recently, Powhatan. I really love this book. Have you read this book? It's really good. It's really good. All right? Another book on likelihood. All right? Another book on likelihood. So I'm going to talk about likelihood because of the following. So for my first dollar, because nobody said anything yet, and you can stop me at any time, but let's get some going here. All right, who is that? Anybody know who that is? Fisher. There you go. Fisher gets the dollar. All right? It's Fisher. All right? So what has Fisher got? All right? So what's Fisher got to say about this? Well, this is Fisher, all right, and he believed whenever we can, we should use probability-based inference. Probability-based inference. Likelihood doesn't do that, all right? So what he said is using likelihood alone provides a weaker form of inference than probability-based inference. So if you're a likelihood ratio fan, I'm going to take exception to you because we get these high likelihoods, but we don't have a probability argument to go along with it. And you can have high likelihoods even with things that still have low probability. And I'll show you an example of that. All right? And this is all from Powhatan's book. It's really a great book. Another dollar.
Feynman.
Huh?
Feynman, Richard Feynman.
Who said? Oh, no, you don't get another one. No. You're not going to get rich on me. Yeah, this is Richard Feynman. So Richard Feynman is one of my heroes. All right? Richard Feynman, and what he said was, scientific knowledge is a body of statements of varying degrees of uncertainty. Oh, this is so nice for statisticians to hear from a physicist, okay? Some mostly unsure, some nearly sure, none absolutely certain. Those of us who are old enough, we remember the American Stat Association used to sell a t-shirt saying, being a statistician is never having to say you're certain. All right, so here it is again, all right? March of Science. So I've transferred this into something. I just did it for my teaching, and it's caught on, and people, they tell me I get credit for this, and it's sort of crazy because it's just this little gag that I do, but I call it the March of Science. And it's, we put now hypotheses on a probability scale. So here's the touch of Bayes coming in here, all right? So on a probability scale about whether or not the hypothesis is true, we can have mostly unsure down there. We can have nearly sure down there. We can have certain down at the end, but of course certain is also at the very beginning. We can be certain that the null hypothesis is not true. All right? So we're back to the stat fable again. And you remember the design. And we're going to base this on a paper because I want to make sure you understand that the foundation of this begins with a frequentist method. So this is a frequentist method to compare two proportions. A problem that's been around in statistics since the time of Pearson and before that and all that kind of stuff. Very hard problem, actually. Here's the latest paper that I know. It was published in December. So I'm at the beach in North Carolina. I get the PDF and look at this and say, oh, here's the latest paper on how you compare two proportions. I'll program it into R and I'll make it the basis for this so people can see that it's based upon a frequentist method. All right? So here we go. Based on a frequentist method. Now, here's the mortality difference, bias 266 versus usual care. And I've set up an essentially null interval, and I've set it up between a minus 2% difference and a 0% difference. Thinking that if the difference is in there, it's not going to be worth anybody's effort to now take this into Africa or whatever it does. You can form any other essentially null interval you want. You can form an essentially null interval between that pixel and that pixel if you want. I don't care. It just needs to be an interval mathematically for me to make an argument. That's all. I'm just picking this one just for illustration. Now, the touch of Bayes comes in because we're going to put a prior probability in that interval. we're going to put 0.95 as a prior. I'm going to say, you know, I'm going to say 0.95 in there because I'll use the pointer, I don't use it much. We want some prudent scientific skepticism to come in here. Prudent scientific skepticism. What do we do as scientists? We start off thinking the null is true, and we have to make the data try to get us outside of that. Well, I'm coming with an essentially null interval. I'm going to put a 0.95 in there, and to make this look as close as possible to what we do in frequentist testing, guess what I'm going to do, of course? I'm going to put 0.25 and 0.25 in the two ends. You get it? This is where we start. This would be negotiated. This was a clinical trial. We'd talk to the FDA. We'd get our study sponsor on board. We'd set this down in paper, and we'd leave it. The entire rest of the process, everything else we do, is based upon a frequentist test statistic and the data. There's no other Bayesian stuff that goes in here. None. Zero. This is the beginning. Yeah?
When you make those probability assignments, I can understand 0.95 spread uniformly over the interval. How do you spread the 0.025 over the...
I'm not spreading it over. Everything I'm going to do is going to be based upon likelihood ratios of... I'm not going to go into the theory, but the likelihood ratio, suppose the result comes out over here, whatever this scale is, okay? I'm going to take the maximum likelihood estimate of the density here, and what you have to do is you have to come up with a non-centrality. You have to estimate the maximum likelihood for the non-centrality parameter. You take that, you compare it to that, and you compare it to that. That's how you're going to see the examples in a little bit. I'm not putting density over the whole range. Okay? I'm just saying it's either in that region, or that region, and I'm taking the maximum densities that I can get in those regions relative to the data. All right? That's the math behind it. But I've never shown the math to anybody. But it's basically a bunch of maximizations that goes on, and you have to do iterations in order to find out where things are and whatever. The math is not important here. The concept is important. All right? But you get $1 anyway.
Thanks. So these are probabilities?
Another $1. Go ahead. These are prior probabilities.
So you would go to your funding and say that our probability is a 95% probability that we will find nothing?
95% probability that you're wrong. Okay? You think you're on the right track because you wouldn't be doing this study anyway, but your prudent scientific skepticism says, follow the example with me. You want to start here. You want to start with something that's against your notion, and then you want the data to overcome that. So let's do the example. You're right with me, believe me. These questions are the perfect questions. You're right with me, all right? But let's see what happens. Let's see what happens. Let's carry it through. This is where we start. Trial number one. Trial number one, the guy has the idea, I think this stuff will work. I got enough money to go to Africa, but it's the end of the rainy season. I'm going to go there. I'm going to set up a small tent. I'm going to give these kids this stuff, and let's see what happens. And so he gets about 70 in a group. He's got 21 that died in the BIOS 266 group, and he's got 31 that died in the usual care group. Simple? Simple? All right? And then this is all output from an R program that I have, okay? So what we have here is the sample size, all right? We've got the two proportions. You'll see the data come up in a little bit. We've got the estimate of the difference between the two proportions. The z-test based upon that article that I showed you from the American Statistician of December of 2010. We've got a p-value. We still have to have p-values. Damn it. All right? And we've got a confidence interval. So let's look at what it is. For this particular data, we've got proportions of 30% in one group and about 45% in the other group. Looks good, right? This is in the direction that we think things ought to go. All right? We get a test statistic that gives us a p-value, a z-statistic gives us a p-value of 0.07. Oh, it's non-significant. You know, it's just non-significant. That'll come back to haunt us if we're in the traditional world today. All right? And we get a confidence interval that goes from minus 0.304 to plus 0.01. And so I'd be saying to my students, why is this related to the p-value? Well, it contains 0, therefore, you know, blah, blah, blah. Okay? Don't have to do it with this group. Well, what we get out of that, in answer to your question through an example, is we get out Bayes factors for the 3 regions, okay? So these are the 3 regions compared to each other, taking the maximum density that we would have gotten, given the data, in each of the 3 regions and contrasting that. That's basically the crux of the theory, okay? So we've got the 3 regions, the superior region, the null region, and the inferior region, all right? And we got Bayes factors of 3.35 because it's over on the left-hand side. That's where it was, all right?
But by Bayes factor, you mean the posterior for one of the 3 sets over what?
This is just the Bayes factor. This is just what is, okay, I got a result, okay? If I fit the best, in this case, Z distribution for that result, it'd be actually the height of the normal 0, 1 random variable. That's my maximum value.
So that was taking the maximum likelihood over the restricted parameter space?
Yes. Yes, it's the maximum likelihood over the 3 parameter spaces, okay?
Where do the weights come in? Where does the 0.95 and the 0.02?
That comes in through Bayes factor because you get the likelihood ratios and you multiply them by the odds that I've set up there with the 0.95s and the 0.25s, and then I get out the posteriors. It's a very simple calculation. So there's the Bayes factor, which says, quote, without any priors on it, we're 3.35 more likely to be in this region. But if you don't put priors on it, you don't get any probability base. That's what Fisher was saying, okay? Well, you're 0.3 over here and you're 0.2 over here because you're further away from the result. The result is on that left side, on that beneficial side. Well, you can transform, all right, you can transform that into posteriors. And so you flip these to posteriors. Remember what the priors were. We just went through them. So now this went from 0.25 to 0.085, okay? It was a small sample size in an okay result, so it pushed it a little bit along, all right? That went from 0.95 down, and it's way away from this one, all right? And so it went from 0.25 to 0.005, okay? And so that's what we're talking about there. I guess I should use my pointer. I spent all that time doing that. All right, so here is a summary of where we are. We start off with these, all right? And now we update them to 0.85. 0.005, and 0.91. Isn't that easy? Working with an investigator, don't have to do p-values. You say, here's where we are. I mean, you've got to go through the negotiation on where you start, but all the rest of it is data-driven. So these are posteriors, all right? And now what we have is a little picture. Remember the March of Science diagram, all right, after the Feynman quote? And so we're going from 0.25 to 0.85. Before trial 1 to after trial 1, that's all data generated, okay? And so science marches forward. And so we got our little guy, and he marches forward. Oh, come on. Isn't that cute? Yeah, question?
You call these posteriors, but are they really posteriors? They're really not Bayes calculations.
They're not the same kind of Bayes.
I would not call them posteriors.
Maybe I should think about that.
You know, profile likelihoods adjusted for...
I think you know more about traditional Bayes than I do, and that's one of my weaknesses, yeah.
Well, actually, Richard Royal is one of my colleagues.
Oh, okay.
I thought he did a really good job on the likelihood principle.
Yeah, he did.
Yeah.
He did a great principle, but he stopped short of putting priors on those regions, so he doesn't go to probability based.
Exactly.
Yeah.
Can you go back one slide?
Mm-hmm.
To your little march?
Yeah.
Okay, so if you're talking to the investigator,
Yep.
or Dr. Chance is talking to the investigator, what is your interpretation now for that 0.085? How are you interpreting what that 0.085 means?
I'm 8.5% sure that BIOS 266 is superior, but only 8.5%. Okay? So what would you do? What would you do if you were here? You'd run a second trial, right? He gets some money. He says, hey, we got some pretty good results on the first one. He gets some money. He goes back to Jamcatnia. All right? That's where he does this study. That's Jamcatnia. My daughter's names are Jamie and Katie. All right? Goes back to Jamcatnia. He's got a big trial here. He's got 300 kids in a group. All right? He gets the following results. He's got 12.5% difference between the two groups. It's a big trial, so he's got a nice, significant p-value there. He's got a 35 point, almost 36 Bayes factor using this method. He's now pumped that 0.85. It's now up to 0.77 as a posterior. All right? And so we update those as follows, and we're pretty happy. Not happy enough maybe for the FDA. We'd be in a touch, would you approve this drug with these kind of things, but let's say not. And so what we do is we run a third trial. We go back to Gemcatnia for a third rainy season, run it again, all right?
Are those numbers for combining both trials together?
Yep.
Okay.
Yep, you begin with the 085 and you're updating it. Yeah, you begin, because now you're just like in traditional Bayes. Your posterior from your first is now your prior for your second.
But there are two calculations you could possibly do. I don't know if those are identical. One of them being that you could collapse the data together into one table.
Yeah, no, they're different.
Yes.
They would be different.
And that's the point about the Bayesian, is
Yeah.
it's always coherent. And your calculations are not coherent.
No, they wouldn't. No. It doesn't matter which order I put the studies in.
Right.
Yeah. But you also have to remember that the trials are never going to be exactly the same as each other anyway. And I think that data pooling, I think it really hardly ever is able to be done. All right? But you could say, well, at least I'm at this prior. Yeah, not as simply as that. Yeah, this is a pretty contrived example where we're going back to the same place and running the same drug and whatever. No, you're right. So what do we got? We got our guy marching forward. He's now 3/4 of the way down the entire march. So he goes to trial number 3. Trial number 3 was supposed to be 300 cases in a group, but there was a drought in Africa. And I actually worked on a study when I was at the University of Florida. We were doing a clinical trial on malaria in Africa. They went over there and there was a drought. All right? And all that money really went down the toilet. Okay? So what we got here is, all right, we got about 120 odd observations in a group. We get the following results, sort of the same thing we looked in before. We got another non-significant p-value. All right? We got a superior Bayes factor. But look at what happens. Even with this aborted clinical trial with a non-significant z statistic on comparing the two proportions, we've now got a posterior probability up in the 91.5%. All right? And so now we're updating. We're going from 0.77 all the way up to 91. 0.85, and we're really down to nothing over here, all right? And so now we got our guy marching forward to 0.91, and now, and I asked my best friend today, who's professor of religion at University of Miami, Steve Sapp, I said, would you, and his area is also health, I said, would you approve this? And he says, absolutely, because he looked at the 0.91, he looked at the 0.09 under the null, but he saw that the null was all the way over on the efficacy side or whatever, and he saw the less than 0.001 on the harm side, and he said he would approve that. So if Steve will approve it, I'll approve it. All right? So here's some remarks. The two sides of the hypothesis are kept separate. Two sides of the hypothesis, none of this two-tailed test business, okay? There's no point null, no p-values to interpret. Only one of the 3 trials yields a 0.05 or less, all right? But each move the march forward. That's important because if you know what the FDA requires, they require two well-done trials with p-value less than 0.05 to approve, okay? Although trial number 1 was a preliminary study, its results were fully incorporated into all subsequent analyses. The remarks. Trial number 3 was weakened by low recruitment, but still proved very, very valuable. No need to alpha spending here. We're testing one hypothesis. We're just moving along. We don't have 0.05 that we have to divide up along all these interim analyses and all that kind of stuff because we're not playing the p-value game. We're just assessing the same hypothesis over trial time. The ordering of the study makes no difference. So the studies are exchangeable, like I said, and it has to be that way. It wouldn't make any sense any other way. All right. So what if trial number 2 would yield the opposite results? If we just flip those, what do you think would happen? Well, those are the opposite results. Remember that was minus 125 before. All right. P-value is going to be the same, obviously. I've just flipped the 2 groups. Now what you get is you get a Bayes factor of 0 on that side. And now that posterior went from 0.85 down to 0. And so what you have here is obvious, okay? And now what you have is this guy marching backwards. And that's what you would expect to happen. The method works, and it works with common sense, all right? Here's another a priori setup. So suppose you didn't like that setup. Let's do this one very quickly. So here's a range where we're not good enough or essentially null, okay? And we're going to make that the -4%. So now we're going to say this isn't marketable unless I can get it down to -4% or less, all right? And so we set up, this is now a tougher criterion. It's going to lead to lower posterior probabilities because the criterion is tougher to get to rule into clearly superior. We're going to also change the probabilities. I have complete flexibility here. I'm going to put 8.80 over here, all right? I'm going to put 0.5 over there. I can do anything I want. And I'm going to put 1.5 over there. And I'm going to argue this is just another case of prudent skepticism. I'm now loading things up against the hypothesis that I want to confirm, all right? And I'm loading things over here because if there's anything inferior about this, I want to pick it up faster. I want to give the Bayes method, the Bayes factor, some teeth, all right, to get off and started over here. So let's see what happens. I'm going to take you through this. This is the same data now. I don't have to go through the data part. Same data beginning with this set of priors and this structure, all right? So 0.5 goes to 0.143 after trial 1. Trial 2 goes 684. Trial 3, 813. Should we run another trial? Some people would say, yeah, you're not far enough along on the march, all right, to do this, so let's run a trial 4. We can go back and run a trial 4. Substantial funding. Let's suppose we got funding for 3 sites. Big trial. The sponsor says, I'm tired of messing around with this. We're going to get the answer, all right? So now we got 750 in a group, all right? We got p-values down now to 5 times 10 to the -5th. You like that? Those in genetics, that's not even small enough, all right? Got about a 10% difference. Nice Bayes factor. Now our posterior probability on the superior side is 0.99, basically. We're basically for all the way down, all right? All right, so that's the big example. Now that's the contrived example. Now here's 2 real examples on how it works. So Will says, haven't you been critical of some studies by Dr. Stephen Nissen? And Maxine says, that's correct. I think his 2003 Super HDL trial exemplifies the problems I see all the time. So here's the paper from JAMA, November 2003. I always preface this, and especially when it's being videoed, okay? I was at the Cleveland Clinic. Dr. Nissen is chairman of cardiovascular medicine at Cleveland Clinic Foundation. I was at the Cleveland Clinic when this study came out. I was teaching a group from cardiology when this paper came out, and I used this example in that. So it's not like a Case Western professor's bashing. If you know the tension, let's put it this way, between the 2 institutions, you'll understand why I'm making that disclaimer. I think it's a real good study to understand some basic principles about what goes on in hypothesis testing. It was a preliminary communication. It was a small sample size, as you'll see. Dr. Nissen's question is, does super HDL reduce percent atheroma volume in patients with atherosclerosis? Very straightforward hypothesis, all right? So here's a little diagram. This is a cross-section of the vessel that's occluded, all right? Here's the outside of the vessel here. Here's the inside of the vessel, all right? This is the luminary where the blood flows through, lumen meaning clear or light. Here's the transducer for the intravascular ultrasound. And what you do is a very simple calculation. You do this 10 slices, and you use Simpson's rule to compute a percent atheroma volume. And so it's just dividing a denominator into a numerator. And in this case, the numbers are there. That's not really important. All right? And it's a 56% inclusion. You've all seen these, you know, he was 97% included or whatever. This is a 56% inclusion of this particular image, of this particular slice. As I said, they do 10 of these. They feed the catheter up. They do 10 in the particular area, and they get a number. All right? So what's super HDL? Super HDL is the technical name for it is recombinant ApoA1 Milano. The study name is ETC 216. There's a picture of the vial that it came in during the trial. All right? The design and measurements. Now I'm simplifying the trial, okay? This is simplified from the 2003, which is which was a trial that compared placebo versus 3 dosage levels. The sample sizes were very small. They never really compared the placebo versus the dosage levels. They only compared pre and post, but they lumped everything together. They lumped out the dosage levels together. And so here we go, all right? I guess it was 2 dosage levels, high and low, sorry. So here's a reduction, as you will, of the design. Sample size of 47, 11 went into placebo, 36 went into one of those doses, which they then lumped together, all right? They waited 5 weeks, they got 5 weekly doses, and they looked at the percent change in atheroma volume. So if you went from 56% down to 50%, that would be a 6% difference, okay? Straight difference as it was before. So the analysis that I did, all right, I asked Dr. Nissen for the data through email. He wrote me back within an hour. He said, no problem. He would put me in touch with Kathy Wolski, a name you'll hear in a little bit. Kathy Wolski didn't write, so I wrote Dr. Nissen back. He asked me a bunch of questions. I answered like what I was going to do with this, and I answered the questions. And then he wrote back and he said he wasn't going to give me the data, okay? So I tried to get the actual data, so now what I'm doing is extrapolating off of numbers that they gave in the paper. So let's use a Welch t-test to compare 2 arms on the absolute change, not the relative change, absolute change in percent atheroma volume over the 5 weeks. So it's similar to what he would have done, I think, if he had analyzed this way, but he didn't. The analysis, super HDL versus placebo. All right, sample size I've given you before. The mean difference was minus 1.2% in the hypothesized direction. The standard deviation was about 3. All right, 95% confidence interval, minus 3.5 to 1.1. T-statistic Welch T, p-value 0.28. P-value 0.28 comparing drug versus placebo. All right, again, based on table 2 of the Nissen paper. All right, so how would your new method apply here? Well, we can set up a region, all right? And so we'll set up a region, and this one looks pretty reasonable. All right, we'll set up essentially null, and we'll say that anything between 0 and minus 0.25%, a quarter of a percent change, all right, is in our essentially null region. You can pick any region you want. I picked this one for show, all right? Over there, super HDL is inferior. So no, notice I don't have any, like I did in the other example, I don't put any essentially null region over the inferior side. I just made, you know, whatever it is. All right, super HDL clearly superior over here. We're going to put 0.95 here like we did before. We're going to put 0.01 over here, and we're going to put 0.04 over here to be very skeptical. We can do anything we want. That's what I'm doing here, all right? Very skeptical priors here. Very skeptical priors. And Will says, wasn't Dr. Nissen very skeptical about the super HDL hypothesis? And Maxine says, yeah, you must be remembering what he told the New York Times. So here's what from the New York Times of November 5th, 2003, and the week following the publication of this paper. This is the first sentence in the New York Times piece. Here's the title, Cholesterol Study Offers Hope for a Bold Therapy, written by Gina Collada, if you know who she is. She won an award a few years ago for her reporting, award by the American Status Association for her reporting. A small study of heart disease, studying a hypothesis so improbable, its principal investigator says he gave it a 1 in 10,000 chance of succeeding. Now, somebody who's been thinking about this problem for a long time, this was like music to my ears. New York Times, first line of a New York Times article, and we got a Bayesian prior on a null hypothesis. All right? So here we go. Will says that seems like a prior for the superior hypothesis of 0.0001. Doesn't it? 1 in 10,000? All right? And Maxine says, yeah, but it was purely hyperbole. I'll give him the benefit of the doubt. All right? So here are our priors. And if you take the data from table 1 and you mash it through the Welch t-test, okay, you go from 0.01 to 0.015 with this data. You saw the p-value was 0.28, right? So it's, you know, it's not going to move much. And that goes down, or actually that goes up to 0.962. And since it was on the efficacy side, the inferior side drops about half. So it makes pretty much sense, all right? So this would have put Dr. Nissen's hypothesis a tiny step forward on the march of science, right? Right? And Maxine says, exactly. A little tiny step forward from 0.01 to 0.015. What if Dr. Nissen had been much more optimistic? Okay, let's consider the following schema, which reflects what I call statistical equipoise. All right? So what's statistical equipoise? Well, we're going to have 0 here, all right? And we're just going to put 0.05 on one side and 0.50 on one side and 0.50 on the other side. Hey, if I don't believe that the null hypothesis is true because these are two active and I'm now indifferent to which side, I could change that if I want to, but that's balancing harm versus benefit. I start there. I can start anywhere I want. I can start there. So what do we got? If we run table 2 through here, we got from 0.50 to 0.65, and of course that's the 1 minus thought. Easy to understand, easy for investigators to understand. So all of this should have encouraged additional studies on super HDL, right? It's in the right direction. Should go back to that little pharmaceutical company in Ann Arbor, Michigan. 5 people owned it. She's from Ann Arbor. She went to school. 5 people owned it. They didn't have a single drug on the market. That's who owned the patent for this. That's who sponsored the trial. All right, this small little trial. 5 people, nobody owned it. No product on the market. 5 people own the patent. All right? Right. Isn't that easy to work with? Then Maxine says, but an amazing thing happened within a few weeks of that article's appearance in JAMA. Here's from Forbes. Pfizer to buy artery Drano. All right? New York-based Pfizer Corporation has agreed to pay $1.3 billion in class. I'm sure Ann Arbor must have been real happy there. It got 5 guys that just got $1.3 billion for a product with a p-value of 0.28. I'm telling you, it was unbelievable. All right? Now, I was teaching cardiology at this time, so I was following this. That's where I got all this stuff. So here we go. And the news report says Forbes, the first medicine ever shown to actually reduce the amount of cholesterol plaque in arteries. Actually shown. Did you see any data there that says actually shown? All right? All right. In collaborating with you before, all right, you know, I'm going to skip this for lack of time. I'm going to just whip through this.
I would like to see the confidence interval.
Okay, let's do the confidence interval. In collaborating with you before, you've always stressed the need to use confidence intervals. Okay, I've got a simple idea for that too. All right? So I'm undecided. Look at the wording here that I've used because I'm undecided how to get this estimate yet. All right? I've been working on it. Things just aren't working out, but I'll get it there. Some point estimate for the effect, okay? Some point estimate that I got across the trials or whatever for the effect. And then what I need to do is I need to find some factor delta, which I can easily do now just through iteration. Some factor of delta, all right, that if this were now the null interval, if you will, that would take that null interval from a prior of 0.05 to a posterior after all the data's in for all the trials that I had to 0.95. And that's what I'm calling a 19-to-1 support interval. You see the 1995 versus 5, okay? A 19-to-1 support interval. I'm calling it a support interval because I can't use confidence interval, I can't use credibility interval, obviously, but I can call it a support interval. So that's support for the hypothesis, all right? That's where the 19-to-1 comes from. So here is the Nissen data. I told you the point estimate was, well, it's only one trial, so the point estimate is minus 0.12, all right? And the 2 intervals we got, which take it from 05 to 95, are from minus 4.2% to 1.8%. So that gives us a region where the data would have supported going from a prior of 05 to a posterior of 0.95, and it's a wide region because this is a big, big change, okay? We could also, you know, the confidence interval, if you remember, was minus 3.5 to 1.1, the standard 95% confidence interval. So if you want to compare 4.2 to 3.5, so it's wider than that. And I would expect it to be wider. It's a more stringent criterion than the 95% confidence interval. We could do a 9-to-1 support interval, which would take it from 10% to 90%, starting off with 10%, going to 90%, and you're going to get a shorter interval, just like you do in confidence intervals. It's less support, therefore your interval's tighter. Very similar idea. All right, so Will comes back and says, it seems that Pfizer did not complete any studies that got exciting results, or we would have heard about them by now. This was in 2003, remember? This is now 2011, so we got a lot of time between those and nothing was heard about, all right? Yeah, said Maxine, you may be right. Consider what happened next in this saga. Now, this isn't made up. You'd think this was made up, but this isn't made up. This really happened, all right? Early 2010, so this is about a year ago, Pfizer sells Super HDL. Pfizer sells Super HDL to the medicines company for $10 million. So Pfizer gets basically 1 cent back for every $1.30 invested. Now that's just on the buying of the patent. We don't know how much money they spent on further testing or whatever. Okay? It's incredible. It's incredible. All right? So isn't Dr. Nissen a major player in the Avandia story? If you've been following the Avandia story over the last summer, he was on the news all the time. All right? I'll tell you what, okay, Avandia is a drug for type 2 diabetes. Very successful drug for type 2 diabetes, all right? But what Dr. Nissen did, I'll show you. What Dr. Nissen did is he did a meta-analysis. I'll show you the meta-analysis, okay? Yeah, he's quite outspoken on this matter. Actually, it makes for another good example of how this new method can be used. So I'm going to show you a clip from ABC News.
Today, a drug implicated in tens of thousands of heart attacks and deaths over 8 years was finally restricted by the FDA, and it happened because of one crusading doctor. So what does this say about the safety of the other drugs on our shelves? Lisa Stark sought answers.
The battle against the diabetes drug Avandia has been long and hard fought. Leading the charge, Dr. Steve Nissen, a cardiologist at the Cleveland Clinic.
People have been asking me today, don't you feel vindicated? And this is not about personal vindication. It's about doing the right thing for patients.
It was Dr. Nissen who first raised the alarm about Avandia in 2007. He found the drug increased the risk of heart attack by 43%. The FDA had approved the drug 8 years earlier. So what was the agency's response?
I became, their enemy for challenging a drug's safety.
The battle lines were drawn. Drug maker GlaxoSmithKline and some at the FDA insisting Avandia was safe. Dr. Nissen insisting it wasn't.
That means a lot of people are going to be put at risk here.
Ultimately, one FDA researcher determined the drug may have caused as many as 100,000 heart attacks, strokes, and deaths. Despite today's victory, Nissen says the war is not won.
I will sleep better tonight, but I will not sleep until I know that we've improved the way we handle these kinds of problems in the United States. We've got to fix the FDA.
Fixing the FDA, says Nissen, means a wholesale change. No longer should the same people at the agency who approve a drug be the ones to decide if it gets pulled off the market. It's a conflict of interest.
We must fix those flaws or we will have further problems like Avandia,
which Nissen calls one of the worst drug safety tragedies in our lifetime. Lisa Stark, ABC News, Washington.
This is from a couple months ago. Not even that. Glaxo's legal problems lead to a new $3.4 billion charge. The British drug maker, again from the New York Times, British drug maker GlaxoSmithKline announced Monday that it was setting aside $3.4 billion, wiping out fourth quarter profits to pay for United States government investigations and product liability cases over its marketing of the diabetes drug Avandia. What the FDA did last summer is they allowed Avandia to continue to be sold with a warning label from hell, okay? Basically saying, don't use this if you can find anything else to control your diabetes. That's basically sort of what it said from what I know, all right? And so if you'll see probably now that you've heard this talk or whatever, you may see ads in the paper or whatever, if you've been on Avandia and you had a heart attack or whatever, call this law group and they'll help you out. Well, they're setting aside $3.4 billion to do this, all right? Dr. Nissen was also a major player in another controversy called Vioxx. All right, so he's a rabble rouser, and that's his calling. All right. So here's the New York Times. Avandia has been controversial since a 2007 analysis linked it with, quote, this is quoting from the New York Times, linked it with a 43% increase in the risk of heart attacks. Man, that's a lot of heart attacks, all right? The lead author of that study, Dr. Stephen Nissen, chairman of cardiovascular medicine at Cleveland Clinic, said Monday that he was not surprised at the added billions of cost to GlaxoSmithKline. Millions of patients were exposed to Avandia during 11 years on the market, he said, resulting in 50,000 or more excess heart attacks. We heard 100,000, I think, on the ABC News clip. He said in an email, most of these events occurred during a period of time when GlaxoSmithKline was aware that the company's own research demonstrated a hazard for the drug, but they failed to warn physicians or patients. Those are pretty serious things that he's saying here, all right? Here's his New England Journal of Medicine paper, all right? The effect of rosiglitazone, that's Avandia, all right? On the risk of MI and death in cardiovascular cases. This is the famous now, Nissen and Wolski 2003 paper. Here are the results from that paper, Avandia versus control for heart attack, an odds ratio 1.43 with a confidence interval, you'll notice from, must be wrong. Why is that confidence interval? Oh yes, no, that's right. 1.03. I just failed my own oral exam. Confidence interval from 1.03 to 1.98. All right. And for death, it's an odds ratio of 1.64. Confidence interval capturing 0. All right, or capturing 1, and p-value of 0.06. So this is sort of the study that launched 1,000 investigations, if you will, all right? Big time, all over the news. The news had this on every single day for a couple of week period when the FDA hearings were last summer. So here's a paper that was published out of the, actually out of L.J. Wei's. L.J. Wei is the last author on here, and I've heard L.J. speak on this. We teach together in a course in clinical trials, and he uses this example. And it's a piece written by, first authored by his graduate student, Lu Tian. Okay, so Tian in 2008 published a paper introducing a new statistical methodology to handle these kinds of meta-analysis, and they used this as an example. Why did they use the Nissen and Wolski 2003 paper as an example? Well, here is from the Tian paper. Here's the sample size of 2003. I'm going to blow this up for you. All right, so here's the rosiglitazone group, the Avandia group, here's versus the control, and here is the first, here's the first study that they looked at. They looked at 48 studies. 357 patients in this study had 2 MIs and 1 death. Notice the small event rates here, very small event rates, okay? But also notice, okay, that some of these trials, in fact, trial number 2 and 3, okay, had 0 events, all right, in death, all right? 0 events on death. So I've been able to handle that problem for a long time. Maybe not perfectly, but I can handle that problem, all right? The way they handled it was to throw every study out that had 0 events in both groups. Just threw them out, okay? So here's some graphics from the Tian paper. This is all from the Tian paper. So here's the Nissen and Wolski analysis for heart attacks, okay, MIs, okay? And what they've done is a forest plot, and what they've done is they've left out all the 10 observations here, the 10 studies, where they threw them out, all right? So over here is the benefit for control, and over here is a benefit for Avandia, all right? And there's the confidence interval and p-value that I told you about, all right? So if you do it on risk difference and not on odds ratio, you get this. And some of us would argue that the risk difference is a more meaningful thing to do because you can translate that into number needed to harm. So you remove this 10 studies and you do the Nissen and Wolski analysis, and you get a similar result on risk difference of 0.03. So what the Tian group did is to reanalyze this, all right? they reanalyzed it with a method that puts all of the 0 events in there, which of course is smack dab on the null hypothesis, all right? And what we got here is, if you put the 10 studies now in, we've got a risk difference of 0.18, and we've got a p-value of 0.27. So you put them back in with this new methodology that the Harvard group had, and that's what you get. Here's the same thing for death. So for death, here's the Nissen-Wolski analysis, which I gave you before. All right, for odds ratio, here it is for risk difference. It's at 0.05 for risk difference. Basically the same. They're all removed here. 25 studies. 25 of the 48 they threw away for this analysis.
Even for the original reported odds ratio?
Mm-hmm. Even for the in the New England Journal. People always ask me, how did this get published? I said, I don't know. I didn't review it. All right?
Did they report that in the paper?
Yeah.
They threw out
Yeah.
the studies?
Yeah, they reported it. It's right there. It's one-liner. It's a one-line sentence. There's no, they disclosed everything. I mean, all the criticism that I've done today of Dr. Nissen, and I haven't done any, I haven't said that there wasn't disclosure or anything like that. It's just, you know, so I've never charged anything like that. If you analyze it with the Tian method, that p-value goes to 0.83 on risk difference. Their method is for risk difference. So, all right. So here's some confidence intervals to look at what we got so far. For Nissen and Wolski, that's what those confidence intervals look like for MI and for death. And if you do the Tian, that's what those confidence intervals look like. So here we're in the dilemma of which method to use, blah, 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 blah. But obviously a method that uses all the data, to me, is going to be better off than a method that throws all that stuff out, because those studies are smack dab on the null hypothesis. Well, Will comes back and says, what would your direct inference method do with these data? Oh, it's certainly direct, says Maxine. All right, so here's the mean difference in percent. Oh, that's crazy. Here's the difference in percent deaths, okay? Oh, no, it is the mean difference in percent deaths because it's across trials. All right, here's essentially null. Here's the essentially null. And I've made it from 0.05%. Let's make sure you understand how small of an interval that is, okay, that I'm calling essentially null. It's a tiny little interval. I just got it in big space up here. It's a tiny little interval, okay, that I'm calling essentially null. Over there, Avandia would be beneficial, and over on the right-hand side, Avandia is harmful. And the hypothesis here is about harm more than benefit, all right? So the number needed to treat at that 0.05% is 2,000, all right? To have one adverse event, 2,000 at that 5% of a percent, if you will. So we're going to do this again. We're going to put 95 over there, put 025 over here. We're going to put 025 over there. What happens in mortality with the Nissen and Wolski data? Now this is the Nissen and Wolski from 2010. They published a paper in 2010 where they added more trials and did a very similar analysis, defended their throwing out, in spite of the Tian paper, defended their throwing out of the stuff. L.J. Way actually wrote a rejoinder to that paper and got it published, okay? And that 0.025 goes to 0.22, the 0.95 goes to 0.963 with the method that I'm advocating today, and basically nothing changes. Now you saw that with mortality. This is the death one. You saw that we didn't get those big of differences, okay? What about MI? What about MI? And the method I'm using here is an exact method. I'm just taking the probabilities given the two binomial densities, because I tried it with that American statistician paper. It just doesn't hold up because it's based upon asymptotic principles, and you saw this just doesn't work. So I just flipped it in, and we're just doing straight binomial likelihoods based upon the two binomial distributions here. Essentially null, all right, we got the same thing. Starting off the same way, with the Nissen and Wolski data, 0.025 goes to 0.080, that goes to 0.11, and that goes up to 0.809. So it spreads it out because you saw the forest plot where the results were spread all along there, so now you see the posterior spread. But this one actually disappointed me, okay? Because that's a big jump in support of Nissen's hypothesis. I will say that with the video going. This supports Nissen's hypothesis going from 0.025, which is a pretty skeptical prior on this, up to 0.81, okay, it looks pretty good. What I was hoping to see in my stilted mind at almost 62 years old and heading to retirement is that, you know, this would be a really low number, and then GlaxoSmithKline would call me on the phone and said, we'd like to hire you as an expert witness. All right, but I don't know if they're going to hire me at 0.81, okay? So that's what happens in science, you know. The slaying of, my hypothesis was, of course, that there was nothing going on here. So you've heard the expression, the tragedy of science is slaying of beautiful hypotheses by ugly facts or ugly data. All right, and that's what that is.
Were those analyses using random effects across
No,
trials?
no, it's just straight binomial. Oh, the Nissen and Wolski one, fixed effects.
No, but yours.
No, I just took them as 50 as, in this case, 56 2x2 tables. Just simple as you could think of, just for illustration. Yeah, no random effects, nothing of that. So, yeah, I'm sure a lot more sophistication could be done, but I wanted to show you that you could use this for meta-analysis because it's the same thing. It's the same idea. Your method gives me a direct way of looking at this whole Evandia question. What else can you show me? And Maxine says, a lot more, but I'm out of time. And then she says, thanks. So thanks.